So this one's actually a equilibrium Newton's second law problem, but it could actually be a rotation problem because a ladder that's leaning against a wall, if this is my wall and this is my floor, actually, when I think about the forces acting on that, I can't just think about the forces acting on a single point. So I could start to do a free body diagram, but remember in the past we've done a free body diagram for just a single point, but for a ladder rotating, we don't want it to rotate. So this ladder, we want it to stay at rest. So I could think about the forces. Number one, I've got the weight of the ladder acts at the center of mass. And please mind my messy diagrams. I'm doing this on a touchscreen laptop with my finger. So then if I look at the wall and the floor, then first of all, we know that normal forces always act perpendicular to a surface. So the floor pushes up and the wall pushes inward. And now we want to think about what keeps that ladder from sliding out on the floor and down the wall. Well, it's friction. So on the floor, if I think about the ladder having a tendency to rotate around the center of mass, then I can think about this ladder rotating in the clockwise direction, or the point that's touching the floor wants to slide out. So the friction force must equal a force going to the right. And then the same thing, if the ladder kicks out at the floor to the left, then that means it would slide down the wall. So that means friction must also act up the wall. So I get all these forces acting on it, but Newton's first law and second law still hold. Some of the forces in the x direction have to equal 0, which means in this case, the only two x forces are the normal force from the wall has to equal the friction force on the floor. And then we could also say the sum of the forces in the y direction have to equal 0 as well. So in that case, the friction force from the wall has to then, plus the normal force from the floor have to both be balanced out by the weight of the ladder. So if we look at the answers here, which of the following has the same magnitude as the frictional force on the ladder by the floor? Well, we already looked at that over here. It has to be the normal force exerted by the wall due to simply Newton's first law. But I wanted you to realize that this ladder problem could be a rotation problem. In higher level physics courses, leaning ladders against walls are quite common problems. But in this case, it's just an equilibrium problem. This problem is a pretty straightforward conservation of angular momentum problem. But remember, understanding conservation of momentum, whether it's linear or angular, is about, first of all, understanding the system. And you're told here that the system contains two things, the disk and the clay. So that means that the change in angular momentum has to be equal to 0 for the system. Remember the conditions. If no net external torque. So no net external torque, just like a linear system, two bumper cars or whatever, would conserve linear momentum if there was no external forces. So we could write this out. The clay, even though it's moving linearly, the clay still has angular momentum with respect to the system. When it hits this, we could think about what would happen. The disk is rotating in the clockwise direction, so it has angular momentum in the clockwise direction. Remember how we would say that? The linear momentum of the disk would be equal to the rotational inertia of the disk times its angular velocity. And then the clay moving, even though it's moving in the upward direction, which is a linear translational motion, but when it hits, it's going to have a tendency to cause the system of the disk and the clay stuck together to have a counterclockwise. So the clay actually has a counterclockwise. So when it hits, it's going to cause, yes, the total mass of the system to increase. Yes, possibly the rotational inertia of the system changes. Yes, the angular velocity may slow down or change directions, but the key here is that the disk and the clay, this is all defined as the system, so the total angular momentum has to stay the same because there's no net external torque. The clay hitting the disk is internal torque because the clay is part of the system. We did this one in class, but we can recap it again. So once again, we're talking about conservation of angular momentum within a system here. So this is very much like the last question that we just did. So if I define my system as the rod and the, whatever this, sphere. So the sphere has linear momentum. So this is kind of the new idea. If an object has linear momentum with respect to a rotating system, then we can also define its angular momentum as its linear momentum times its distance from the axis of rotation. I'm using D because that's the symbol that's used in this question. So we could say the disk originally, or sorry, the sphere originally has, so L initial equals pi d, and since that's going to cause the rod to rotate in the counterclockwise direction, we can call that whatever. We can call that maybe the negative direction. But then when it bounces off, the rod is moving in the counterclockwise direction, so the final angular momentum has to equal the opposite direction. So clockwise, PFD. So the change in angular momentum of the sphere is equal to PI plus PF times D, right? Change in angular momentum. Final angular momentum is PFD minus the initial. Well, the initial's in the opposite direction, so minus a minus means PF plus PI times D. So in order for the total angular momentum of the system to be conserved, if the change in angular momentum of the sphere is PI plus PFD, then the change in angular momentum of the disk has to be the same, right? Because the total change in angular momentum, or the system's, has to be equal to 0. Law of conservation of angular momentum. So we said the answer there has to be D. The magnitude of the angular momentum of the rod after the collision has to be the same as the change in angular momentum of the disk, because the initial angular momentum of the rod is 0, or the rod is 0. We talked about this one in class too, but we can recap it. Remember, impulse equals change in linear momentum, right? And I can define impulse as force times time equals change in linear momentum. Well, we have the same exact thing. If I have a rotating wheel and I apply some force at some distance from the axis or the wheel's moment arm, or the axis of rotation, then I have a torque. So I can have a rotational impulse just like I can have a linear impulse. So I could say that torque times time equals change in angular momentum. Force times time equals change in linear momentum. Torque times time equals change in angular momentum. So if I'm looking for an experiment that would let me see the relationship between torque and change in angular momentum, so I would have to do something. So I could write this as force that's perpendicular to distance times time, right? And that would be torque times time equals change in L. Well, let's look at what isn't changing. It says a disk of known radius. So that isn't something I'm going to change. So if I want to see the effect of torque, The only thing I can change in this situation to actually change the torque is the force. So I also know that the amount of time that's applied dictates the rotational impulse. So the only one here that makes sense is that I want to vary the force, but I need to keep the time constant. So I want to say that force is proportional to change in L, right? So if I want to look at that experiment, I have to keep everything else constant, including the radius of the disk, which it says it is known and constant. And also, importantly, the amount of time that I apply the force, because the longer I apply that torque, the more the angular momentum is going to change. So I won't be able to tell what's really affecting the angular momentum, the changing force or the amount of time. So I have to keep the time constant. So D is the only one that really makes a lot of sense, and that's really just about establishing a good experiment.